ಅಂಗೀಕಾರ ಆಗಿದೆ. ಪಕ್ಷಿಯ
Okay, thank you. Okay, I just started sharing my screen. Let me know when you all can see it at your end.
Yes, sir, it is visible.
Yes, sir, it's visible, sir.
Okay. So I have put together these topics for today, day 4. We're going to focus on characterization of digital logic cells. We will cover about, we will talk about why we need to characterize or what's the motivation. And we'll talk about characterization of combinational logic gates. I will show some examples of how the outputs of the characterization flow looks like for the combinational gates. There's this concept of .libs, which is the output file, which is the industry standard generated from the characterization flow, which is used by a lot of these CAD tools, which is used in the ASIC flows. I'll show some examples. And then also I will discuss about the concept of timing arcs, which I think yeah, I'll cover the concept of timing arcs, and which is basically an important, very basic concept, but important concept to understand when we want to understand a characterization and how some of these concepts may possibly get used in static timing analysis and so on. Then we'll have break 1, where probably we'll have some Q&A based on the topics covered before that. And also, if you have any questions from the previous 3 days, then we can cover that as well. Post break 1, we will talk about characterization of sequential elements. We'll talk about how the flow would look like. Let's say if you just run a simulation at your end versus, let's say, what's the actual industrial flow, which is typical flow which is used in the industry. I'll introduce the audience to the concept of PBT corners. We will may not be getting into too much of detail because I don't know whether the audience has a broad understanding or a deep understanding of all aspects here, but I will introduce the audience to basics of PBT corners and motivate the reasons why it's important to understand PBT corners. And then PBT corners are very, very important, especially if you work in the industry, because I'll talk about this at when we reach this point, and then I'll show a couple of papers where the concepts of PBT corners and the concept of variation across PBT corners is discussed. So it may be slightly advanced, but I think these are like extremely good papers, which if not the basic, the audience with very basic knowledge, but certainly master students and academic lecturers and professors certainly can gain out of it, who would have better background in appreciating the concepts discussed in the paper. And then we'll have break too. And tomorrow's agenda, I think, is something which is probably extremely relevant from an overall VLSI design flow point of view. I'll cover the concept of static timing analysis, power analysis, and optimizations. So let's get started. So we talked about combinational logic gates and also sequential elements yesterday. Conventional logic gates was covered day before yesterday, and we talked about the various logic gates that we can build, how they could be built using CMOS logic style, and how we talked about some concepts of how to analyze the delays, how delay is dependent on outputs, load, and input transition, and we touched upon the concept of logical effort and things like that. Those were all very preliminary concepts in the sense that they could be just done with pencil and paper and or with just formulae. We probably didn't need any simulation tools or detailed analysis required there. But once you actually want to analyze things in lot more detail, or let's say you want to actually build an ASIC chip, or let's say you work in the industry and you want to analyze these cells. So no one is going to do a very first order pencil paper analysis, even though that's useful to understand. But when people have to really see the effects of these circuits and how things like wire delay, gate loads, effect of process, and so on has an effect on the cell's parameters and its various behaviors, then we need to get into details here. We probably cannot do without simulations. So that's the first step. So what we're going to talk about is, in the slide, I will cover about delay and transition of digital transition time of digital gates. So delay, as we discussed last time, is nothing but propagation delay, which means delay from the input to the output. And transition time, specifically output transition time, is nothing but the time taken by the signal to reach from a certain level of its logic level to another lower or higher level of its logic level. So which means, for example, we could go from the output going from 10% to 90% or 25 to 75, as we saw when we were discussing about slews or transition time, rise time and fall times. So basically here, when I say delay, it means propagation delay, and transition time means output transition time. So if I look at a very simple example, let's say there's an AND gate and it has input pins A and B. It has an output pin Z, and it has some load here, a capacitive load, which is this load could be coming from, as we discussed earlier, could be coming from some gates being driven by it, or some wire being driven by it, or a mixture of gate and wire. So some load sitting here. So as we saw earlier, the propagation delay is directly proportional to the input transition time and the capacitive load on its output, which means that if the load increases, delay increases, and the transition time is going to go up, it's going to worsen. That means the delay is going to go up. And as we saw, in a couple of days back, that the reason is because we can think about the delay of a logic gate as a simple RC circuit, which means the delay is going to be proportional to R and C, and R of a gate or a transistor in the gate is dependent on its input transition. The worse the transition, that means the slower it rises or falls, the more the transistor spends in its intermediate state, and its resistance is going to be high. And the quicker the transition is, the quicker the transition switches from its initial state to the later state, and if it is on, its resistance is going to be very small. So both these effects have a direct relationship. I worsen the transition, that means increase this time, resistance goes up, which means delay increases. Or if I increase the load, capacitance goes up, which means delay increases, right? Now, I just talked about delay here, but similarly, transition, again, the output transition is also dependent on the R and the C of the R of the devices or the transistors forming the gates and the load sitting here. But the actual function or the relationship may be different, because even though I've shown an AND gate here, it could be this whole black box could actually have been a multi-stage gate. As we discussed earlier, multi-stage gates means you would have a series of gates one after the other cascading. And so if it's a multi-stage gate, then the transition is only dependent on the final stage, whereas the delay is dependent on all the stages sitting there, right? So therefore, the function or the relationship of the delay and the transition may be different with respect to load and input transition and output load, but both of them have a direct relationship or directly proportional. So if you look at this example here, which I'm showing, so we are interested in seeing the signal propagate from the input A to the output Z, right? Now, I think I was sitting on the next slide for a long time. You may have already seen the answer, but let's see. What should be the logic level? What should be the logic level of B for this transition to propagate from A to Z? Can you just type in the chat? What should be the logic level of B? Pawan says hi. Hi. I'm hearing some background on. Can you please mute yourself? Okay. Organizers, I need some help here. There's a lot of background noise. Can you please help?
Hello.
Sir, you can carry, sir.
Okay, thank you. So yes, we need to have logic high on this because it's an AND gate, which means the only way you can allow this signal's effect to be visible on this is when this input pin B is sitting at 1, which means whatever is the effect on A is going to propagate to the output. So when we are characterizing, so this is basically the requirement. So when we are characterizing a specific input to output relationship, let's say I want to see what is the effect of A pin's input transition on the output, that requires the other pin to be set at an appropriate level. If it's an AND gate, obviously it's going to be logic 1. If it was an OR gate, this should have been a 0. And if it's some other complex gate, we have to set appropriate levels. In some cases, there may not be any easy level to possible. In such cases, we have to run all possible combinations and then see the effect. So, but simple gates, it's very easy. We could easily set the other pin or multiple pins to appropriate states, and we can take care of that. So now, as I was saying, if I run a simulation, so when I say a simulation, I assume a lot of people in the audience already have run or know about circuit simulation. Can you just type in the chat if you are aware of SPICE simulations? Okay, a couple of people have said yes. Yes, yes. Okay, have you run SPICE simulations, or you just aware that SPICE, some tool called SPICE exists? Have you run? Can you just type run, RUN, if you have run it? If you have not run it, say no. Okay, great. So a few of you certainly have run SPICE simulations. So SPICE is a circuit simulator, and that's basically essential if you want to analyze the effect of, if you want to study the behavior of digital circuits or even analog circuits or any form of electrical or electronic circuits. SPICE is the tool to use, and there are different variants of SPICE. There is an a version which is used in the industry, which comes from the company Synopsys, which is called HSpice. But there are a lot of free versions of SPICE also available, PSpice, and then NGSpice, and so on. If you have not used SPICE, or if you don't have access to SPICE in your at home or at college, you can search for SPICE freeware, and you should find some links. And I think if I can probably show that on the last day, and I can try to probably point you to some freeware for SPICE if you have not run it. And I'm assuming that if you're doing some VLSI course, the college should actually provide you the infrastructure for running SPICE, because without that, I think it's going to be very difficult for you to do some complex analysis or publish any papers if you're planning to do so. SPICE is essential. So this plot that I'm trying to show would possibly come from a SPICE simulation. So how would I do that? So the y-axis is delay, the x-axis is output load, and what I'm doing is I'm fixing the input transition to one value, and I am continuously changing the output load. By continuously changing, I mean I fix one output load, I run a simulation. For the given transition, the transition is fixed on A. Then I repeat, change a load again, and run it, which means I'm continuously varying or sweeping the value on the output load. On the x-axis is continuously moving. So as we saw, there is a direct relationship, almost linear, between output load and output delay. You can see that it will be very nearly a straight line. This is obviously just a very representative figure that I've shown. But if you actually run a simulation, you should see a similar figure which is very close to a straight line. And similarly, if you plot, if you fix the output load, and if you change the input transition, let's say from a very small value to very large values, what you're going to see is for reasonably large range of input transition. X-axis again is input transition being varied. Y-axis is output delay. So what you would see is for a large range of input transitions, the delay is almost a straight line. But once you start going beyond certain transition values, there's going to be slight non-linearity, and the delay starts increasing faster. So this depends on what kind of models you have. If it's a very simple model, maybe you may not see this effect. Or if it's just an inverter, you may not see this effect so much. But if it's, let's say, a complex gate, like a AND 3 or an AND 3 or a NOR 3 or a NOR 4, something like that, you may see this effect a lot more. So I will urge you to try this kind of simulations at your end, and to study. One is how to run SPICE if you're not run it, or if you're interested in trying to run some basic characterization at your end. Now, as I was saying, how to generate this data, circuit simulation using SPICE, but also an interesting approach, which I'll come and discuss in more detail, which actually ASIC flows use, is something which is called a pre-characterized delay and transition models. Pre-characterized means it's sort of something which is done offline. Offline means that you've done this characterization work somewhere early in time, and you retain the results with you, and you can use these results to either create a lookup table. Lookup table means like just a mapping. Okay, output load is so much. I fix the input transition and I change the output load. Okay, I have so much delay, right? I can basically create a column, 2 columns which are inputs, 3rd column which is output, and I can map them. So that's one way. That's called a lookup table. Or I can, since the relationship is very simple and linear, or in some cases not far from linear or polynomial, which is easy to model, we could even convert these actual lookup tables or the curves into a mathematical function. So I can build a mathematical function relating the delay to the output load and the input transition. So that's basically the approach, which is called pre-characterized delay and transition and models. Now, before I discuss the characterization, the pre-characterized delay in some more detail, let's quickly try to understand the concept of timing arcs here. So as I was saying earlier, when I discussed about it in the previous slide, I talked about setting B to 1 and looking at the effect of A to Z. So what is this A to Z? A to Z is, even though so A to Z is in A to Z is what's called as a timing arc. Timing arc, because we are trying to see what is the effect of A on Z. So relating an input pin to an output pin is called an arc in the STA terminology. So, and since the characterization is primarily meant for timing analysis, so we will use this, try to use this nomenclature, this terminology, so that you can understand it if I refer to it or use it sometime later, especially tomorrow when I talk about timing arcs. So timing arc basically means a relationship between a specific input pin to an output pin, or between any 2 input pins. So that's called a timing arc. And combinational gates, the timing arcs are always between input to output, most of the times. If it's a sequential gate, sequential logic, like a flip-flop or a latch, there are 2 kinds of arcs. One is an arc between, let's say, the data and the clock, which is an input side arc. For example, you want, as I was showing yesterday, we have something called as a relative delay between data and the clock called setup time. So which means you will have a setup arc, which means data to clock arc. And then you could also have a clock to out arc. If it's a flip-flop, that's an output arc, just like a combinational arc. So sequential arcs will, sequential elements will have 2 sets of arcs, between the inputs and also between input to output. Combinational will only have, or the major arc for combinational gates are between input to output. So here in this example, where we are showing these AND gates here, which have input pins in 1 and 2 and out. So if, let's say, a timing is being analyzed from this AND 1 flowing into AND 2, let's say signal is flowing from, let's say, one of these pins. Let's say in 2 is set to 1, in 1 is the one which is switching or transitioning. Then the AND gate is going to propagate this transition to the output. That's going to flow in here, and assuming the input 1 is set to 1, this pin's transition is then going to flow out. So that means the arc that you are analyzing is from in 1 to out, and then from in 2 to out for the second gate. Right? So the AND 1 timing arcs are, the possible arcs are in 1 to out or in 2 to out. Similarly, the arcs for the out, this second gate could be in 2 to out or in 1 to out. And if I'm specifically analyzing a timing path, as I described, where in 2 is 1 and in 1 is 1, and the transition is happening on in1, then the arc which is active on the path is in1 to out on and1, and then in2 to out on and2. I hope this concept of timing arc is clear. It is very, very simple, even though this seems like something like a technical jargon, but it's very easy to understand since you probably easily understand the fact that if you have to propagate a specific transition to the output, you have to set the other one to an appropriate value, and you should be able to then see the effect of this transition. That effect is basically what's called an arc. Okay, so coming back to this, when we talked about either how to generate the timing data, the generate these kind of data, the plots or the tables as we discussed. So one option was, as we said, we could use spice simulation or the pre-characterized tables, pre-characterized delay or models, delay and transition models, right? So pre-characterization or simulation. How do we compare them, or what's the benefit of one versus the other? So primarily, it's got to do with accuracy versus runtime trade-off. I assume you understand what runtime means. Runtime means how long it takes to generate the results or complete the analysis. So since SPICE is a circuit simulation, its runtime is obviously going to be fairly high, because if the circuit starts getting bigger and bigger, you have to, the SPICE tool tries to see the effect of the transitions on every transistor, and then propagate that effect to the next transistor and keeps looking at it till you complete the simulation. So which means even though it's very accurate, its runtime is going to be fairly high. And therefore, what's done by people is that, or specifically in the industry, is that circuit simulation is obviously, as we understand, is the best approach from an accuracy point of view. But when the number of logic gates is small, let's say, let's say in this example, I'm saying it's 1,000. It could be even 5,000, depending on what's the complexity you're analyzing. But let's say 1,000 is like a good number to which is manageable, and it's the runtime could be, let's say, under 1 hour or maybe not more than 2 hours. But once it starts becoming bigger and bigger, let's say you have a full a very big adder, let's say 64-bit adder, or let's say you have a full a very big state machine of let's say 10,000 states and so on, that becomes unmanageable for SPICE. So in such cases, circuit simulation is probably not the right approach. And also, so I mean, as very clear, if circuit simulation allows you to look at waveforms, it allows you to look at the results and understand how each and every net in the circuit simulation is behaving. So which means it helps you to develop an intuitive understanding of the overall circuit operation. If let's say the circuit is complex, you can run a simulation, look at the waveforms, and you can study what's going on in the circuit at various points in time, at various nets and various transistors, their outputs, various nodes, and so on, right? Especially if you want to study some phenomena which is analog, let's say if you want to see the effect of currents, if you want to see the effect of power supplies, if you want to see the effect of glitching, or if you want to see the effect of power and so on, and not logic, then certainly you cannot do without doing circuit simulation. But simulation cost is prohibitive. It's very expensive, and so therefore, unless your number of gates is manageable, people avoid running circuit simulation. Only very special circuits, or people are doing very detailed and specific analog simulations, that the analog circuits, that's when they go ahead and they are okay with extra run times, and they may be able to run circuit simulation. But usually digital circuits, people avoid running simulations unless it's a very high performance circuit or your tolerances are very, very tight. So the other option with respect to circuit simulation is pre-characterized models. And they are the best approach from a runtime trade-off point of view. So what do we do here? We do something like which is called a divide and conquer approach. So what we do is we run simulation only on the individual logic gates which form the circuit. For example, if you go back to this gate, and let's say even though there are only 2 AND gates here, this is very simple. You can directly run a simulation, but to illustrate the concept, let's say in this case, there are 2 different type of AND gates, AND1 and AND2. So then what we'll do is we'll run circuit simulation only for AND1 and AND2, and then we'll try to understand and capture all its delay and transition characteristics in a lookup table or in a function. And so how do we run the simulation? We will create all contexts. The context means in this case, all various multiple input transition values. As we saw here, we will change the input transitions across multiple possible values from a very small value to a large value with some predetermined steps. And similarly, we can vary the input load and the output load from a very small value to a very large value at some predetermined steps. And that is the context. So once you set up all these contexts, you can create these combinations of input transition and output load and run the simulations for all the arcs which are there for the logic gate. And then you can create a lookup table or a mathematical function, which can then later be used for analysis. So any questions you want to bring it up in the chat? Is this clear? So Pawan, I'll try to answer the question in the break. Just let me know if you understood this characterization part, the comparison between simulation and pre-characterization. Is this clear to the audience? Okay, we'll come back any case during the break. If there are any questions, I'll try to cover that. So how do you set up a simulation for characterization? So people who have worked with schematics, circuit schematics, they may be able to build some digital gate. I mean, circuit schematics are applicable even for analog circuits. So the basic tool is the same. One of the tools which people use is a Cadence Virtuoso. But there are other tools also possible. So you need to create a schematic, and one option is, which typically is what you need to do if you want to do a detailed analysis. You need to take it through a layout from the schematic, and then extract the layout. Extract the layout means find out what is the actual behavior of the transistor in terms of its RNCs, wires, RNCs. All of that has to be captured. So you create something called as an extracted spice netlist, where the transistors, the detailed transistor effects are captured, the detailed wire RC effects are captured, and then that's called an extracted netlist. And then what is done is that is passed to a circuit simulator. So this is one path. Other path is you may not, if you do not have a layout, you only have a schematic, and then from the schematic you can generate something called as a schematic netlist. And then that schematic netlist is again passed to a simulator. So either of these approaches could be taken. So you pass it to a simulator. Let's say the simulator is HSpice, but it could also be a lot of open simulators or free simulators like PSpice, NGSpice, and so on. So you pass it to the simulator, the netlist, the extracted or the schematic netlist, and you write something called as a measurement deck. A measurement deck means, what am I doing to measure? I'm going to measure the input, some input to output arc, a propagation delay, or I can measure the output transition time for that specific arc, or I could measure power, I could measure something else. So along with it, I need to pass something called as a spice model. The spice model is basically the model of the transistors, and if it's extracted, the model of the wires. And the wire is extracted already, then you don't need to have that. You need to pass something called as a extracted wire RC, which is coming from here. So you need to pass the transistor models. Along with it, the spice simulation has to be set up for some transition and load values, as we saw here in the previous slide. Here, you need to say, okay, in my simulation, I'm assuming input transition is so much, output load is so much. So you are passing these values. So there's multiple different values here, multiple different values here. You need to pass them as inputs. So you need to pass them. You need to pass the transistor models and give it to simulator. And in the simulation setup, something called as a measurement deck. You are describing what you're going to measure: delay, transition, power, current, or whatever, right? And then you are describing what is the operating condition, which means which I'll come and talk about PVT, which is called PVT, process, voltage, and temperature. Voltage is very clear because, as we saw earlier, the delay and currents depend on voltage. So you need to know set what voltage, whether it's 1 volt, 1.5 volts, 2 volts, 0.6 volts, or whatever, right? Your choice, that comes from here. That's your specification. Temperature, again, could be 100 C, 50 C, 0 C, depending on what kind of circuit, what your customer requires, or where you want to test the circuit. Its operating conditions comes from you. So you pass this information also, and then you run the simulation. You get things like the timing parameters like delay and transition and so on, power parameters like dynamic power or leakage power. You could also dump out the waveforms, and then you could then use these simulation results to convert it into a characterization database. And this characterization database is called a .lib file. .lib file is basically a standard format. It's basically something called as a Liberty format. It's a proprietary format owned by Synopsys, and but it's something which is opened up for other vendors to use. So, and there are a lot of tools which can take simulation results, can convert it into a .lib format. So .lib format captures some of these parameters in a specific syntax. So that basically is the characterization flow here. So there are multiple possible things which you could measure and run a simulation using the characterization flow, and you could try to find out delay and transition time. I just talked about. There are other things like input capacitance. Why do I need to know input capacitance? Because as I saw here, let's say if I'm connecting these gates, if I'm just running a simulation myself, I need to know, I can say set this load or that load and some value and so on. But if the circuit is connected in a netlist means a connectivity information of various logic gates, then this in so this AND gate is connected to this output, this AND 1 gate, and since this connectivity is there, the information about what is the capacitive load on this pin has to automatically be available when we are running the flow, and therefore this input capacitance is also pre-characterized. So the input capacitance also, and then we can find out what is the internal power. Let's say if it's a multi-stage gate like an AND gate, or if it's a multiplexer and so on. And then we can find out what's the dynamic power, what is leakage, and then if it's a sequential element, we'll have things like setup time and hold time, a lot of other things which you may not even be aware at this point, and even I am not aware of all the aspects, but the flow does a lot of things and it can generate all these information. We'll just focus on the main aspects, simpler aspects, which I think we can discuss in these sessions, which are primarily the ones which I have shown in bold: delay, transition time, input capacitance, setup hold times, and so on. So I talked about the Liberty format or .lib, right? I just described this. This is sort of another view of it. You are varying the input transition, and you are varying the output load. There is a propagation delay. You have a transition time. Could be a fall time if it's a input is rising, if it's an inverter. Similarly, if the input is falling, you would have a rise time. And as we discussed this already, so we will skip this slide. So this slide shows how the actual, an example of how the the .lib syntax internally may look like. Some of you may not have seen this at all. So let's ignore all these aspects because I think you already understand some of it. I described this. So let's look at this portion here, this gray box here. This gray box here, there's a syntax which says cell, which means there's a digital cell. Inverter X1, INV I should say. INV is some name given to the cell, and this specific cell is an inverter. And X1 means what kind of drive it is, which means how it is sized. So the person who may have designed this circuit may have sized this circuit in a specific way, and he may have said that may have called that specific version of the circuit as X1. Usually X1 means that's your baseline inverter, and the next two means it's double of X1 and so on. That's usually the general nomenclature which is followed by the industry. And so in that sense, you can think of it like inverter X1 means it's like a baseline or a reference inverter, and every other inverter is going to be bigger than this by some integral multiple, 2x, 3x, and so on. So pin Y is nothing but the output pin of the inverter here. And then we are saying timing. That means we want to specifically analyze the timing arc relationship for this inverter, which means timing arc means delay arc. Now, what else is given? Cell rise. Cell rise means there is a rise delay. Output is rising. Cell rise means output is rising. It's the propagation delay when the output is rising. And then you have these values here, 0.147, 0.224. And what you notice is there are a lot of different values here. Why are there so many values? Right? How does it make sense? Now, why are there so many values? Can anyone guess? Can people type in the chat? Why are there so many values for our propagation delay? Can people in the audience try to guess, or if they know the answer, type it in the chat? Okay, so let me try to. Propagation delays are varied. Okay, so Sharon, do you want to unmute yourself and describe that? What you mean by that?
Yeah, sir. So in a circuit, we'll be having different parameters. So if my transistor is connected to resistance, there will be a different propagation delay. If it is connected to a capacitor, then again I'll be having a different propagation delay. And if it is connected to a wire and different type of metals also, I'll be having different type of propagation delay.
Okay, so I think that's not the right answer. The reason why that's not the right answer is it seems to make sense that there should be multiple different output connections, and hence we'll have multiple values. But think about it. There could be so many different kinds of metals. There could be so many different kind of metal widths. There could be so many different kinds of gates, so many kind of gate widths. So think about each and everything having n possible values. So if there are m possible variables, we are talking about n to the power of m possible simulations to be run, right? And that's not the way that's unmanageable. Even though that seems possible, but it's unmanageable. So as I was describing earlier, since the only thing which is done for the output is we change the load, just the capacitance. So that means I don't care it's a wire, whether it's a gate or not, because I only care it's a capacitance. So for me, the delay matters only as a capacitance. Additionally, it does not, I vary the transition of the input. Now the fact is that if I have 4 possible values on the input transition, and let's say I have 5 possible values of the output load capacitance. When I say output load, I mean specifically capacitance values. So then that means how many possible combinations will exist for input and output? Can you just quickly just type in the chat?
2 power 5.
Why 2 power 5?
Means 4 input variation will be there, and at the output end I'll be having 5 different propagation delays. So it might be 2 power 5.
But how does the calculation 2 power 5 come about? There are 4 possible values here on the input transition. There are 5 possible values on the output load. So why should it be 2 power 5?
Yeah, sorry, 2 into 5. It might be 20.
It will be 4 into 5, right? 4 here, 5 here. So you fix one
4 into
value,
5.
you have 5 possible values here. You go to the second value, 5 possible values, which means 4 into 5 values, which
20
means
combinations.
20 combinations. Yeah, you can mute yourself. So 20 possible combinations, and therefore, because there could be multiple different input transition and output loads, these values are representing multiple combinations for which we have delays, and that's why you have something like a table. This is what I was describing as a lookup table. And this lookup table, obviously I need to know which variable is representing which dimension, and that's captured in this lookup table template. So there is variable 1, which is input transition, and variable 2, which is output load or the net capacitance, as I was describing. And so variable 1 is usually describing the rows, and the variable 2 is usually describing the columns, which means if I'm going down the rows, that means what's happening? I'm wearing what? The input variable, variable 1. And if I'm going across the columns, I'm wearing
output.
the variable 2. So, and then based on that, you can clearly say that, okay, if my input transition is 1001 and output load is 1002, okay, this is 2, that means second row, and this is third, that means third column, that means my delay is 430. So I didn't describe it, it's 0.43 because the units here are in nanoseconds, which means this is 0.43 nanoseconds or 430 picoseconds. So then I will just say that if my input transition is 1001, output load is 1002, second row, third column, 0.43 picoseconds, nanoseconds. So that's the way people use, or the tools would use these numbers, and that's one of the ways of doing it. This is another example here. Let's look through it again. So here, what you see is there's again a pin Y. It's an output pin. Why do I say it's output pin? Because direction is given as output, and then there is cell rise. With respect to which pin, related pin means which pin is setting up the arc, which means the arc is from A to Y. A to Y. So as we saw earlier, index 1 is one variable, which is input transition. Index 2 is another variable, which is output load or output net capacitance. And so index 1 is determining the rows. Index 2 is determining the column values. And then based on some value which you choose, let's say the third value here, and let's say the fifth value here, you can say that, okay, third row and the fifth value. Okay, I'm going to. So this is cell rise. Again, this is the propagation delay for rise, output rising. Okay, so we'll take a break here, just on time. Let me just check if you understood. Let's say the input transition in this specific lookup table is 0.2. If you notice, 0.2, and the output load is 0.03. What is the value of the cell rise? Can you type in the chat? Let me just type in the chat. Input transition is 0.2. Output load is 0.03. What is cell rise? Okay, I got two answers, which is 0.13. Okay, Banu, do you want to unmute yourself and give the answer why you think it's 0.13?
So because it is in the fourth row or and according to the second column.
So fourth row. Why is it fourth row? 1, 2, 3, 4.
0.2
First
lies
we're
in the fourth row.
1, 2, 3, 4, and then we're saying the second entry 0.03. So which means 1, 2, 3, 4, and this one 0.13. That's right. Okay. So any questions from the content that we discussed today? Anything from the last few days? You can type in the chat. Keep yourself muted. I will call you out if I want to specifically want you to be unmuted. Please type in the chat if you have any questions from what we covered today. Yeah, feel free to ask questions. Please go ahead if you have any questions.
Regarding that propagation delay, that should be
Yeah.
dependent. It's a gate characteristic, as I understand. I'm just not able to comprehend that, if the load varies, the propagation delay also varies. Because, I mean, if I imagine that, the gate in isolation, the propagation delay is an intrinsic characteristic of that gate, irrespective of whether it's whatever is the load after the path of the output. The propagation.
So this is Pawan Ramesh who's asking this.
Yeah.
Okay. So let's try to understand. I think did you attend the session on the combinational gates we talked about?
Yeah.
So did you follow the discussion on logical effort?
Yes.
Okay, so I think if that is if you followed that, then I think you probably should have had this question on that day itself, because specifically, if you remember, we talked about logical effort and what were the two variables that I mean, in this case I didn't talk about transition at all, but the main variable I talked about was output load, if you remember. So here, even though the load is normalized, but it's still output load, just that it's been divided by the input capacitance. So output load has a direct relationship on the delay. Why? Because effectively an RC circuit, let's see if you have some simple diagrams for you.
Oh, okay, it's an RC.
A digital gate is just an RC circuit, right?
Okay.
And as we saw, we are abstracting the load as some CL value, but in reality, the CL has multiple effects. So let's see if I have that. Yes. So when I said CL has multiple, can be broken down into multiple components, right? One is gate load coming from the gates being driven by it, wire being driven by it, but also its own parasitic capacitances, diffusion capacitances from the NMOS and PMOS. I think you are referring to this, but these are major factors here. Why? Because without this, how can you even build a complex circuit, right? So, and since a digital circuit is basically an RC circuit, effectively, so without this load, your delay is primarily just what? Just the parasitic delay. So if you come back to logical effort, this plot, if you remember, y is equal to mx plus c. The m into x component, which is g is, which as if you remember, I talked about the slope, which is m is the logical effort, h is the electrical effort, which is nothing but output load in femtofarad or capacitance unit divided by input load in capacitance unit, so that we make it a dimensionless quantity. So it becomes a ratio. It is representing how much is a load being driven as with respect to how big the gate is. So in a sense, it's being normalized, right? So here, the value when this h is 0 is basically what's the parasitic delay. So the parasitic capacitance coming from the self-loading of the gate by multiplied by the resistance of the transistor is this delay. And whatever is additional over and above this is coming from the straight line, which is having some slope.
Okay.
So this is coming from the load component. This is self delay of the gate. Does that answer your question?
Yeah. So this is the propagation delay itself that we are.
Which one? The
When
P?
we
No,
say
P is
delay,
the propagation delay. That's right. It's from the input to the output.
Okay.
So coming back to our discussion here, let's go
But
back
if
to
there is
slide.
a resistive load, I mean, then also should it vary?
When you say resistive load, like a wire on the output?
Yeah, some resistance on the output.
Yeah, that's a good question. I think so. The point is, modeling resistance is something which characterization does not handle properly. So the way it is done is that when the characterization or the pre-characterization is being done, we only account for capacitance.
Okay.
And then if there is some resistance of a wire sitting here, let's say in the direction that I'm trying to show here, that is something which is handled by the timing analysis tool. You may have heard of STA. There will be some timing analysis tools which get used. The timing analysis tools is then responsible for taking the output transition value which you get from the pre-characterized model, and then it uses some equation to get the wire RC effects, and then sees the effect of a delay over the wire. So the pre-characterization never accounts for any wire resistance.
Okay.
Okay, so thank you. That's a good question. Any other questions? Okay, if there are no questions, let me see if I can ask you some questions from my end. So when we were talking about simulation versus pre-characterization, what were the reasons, what were the benefits of, or what is the advantage of simulation over pre-characterization? Can people give any two benefits of running simulations over pre-characterization? Type in the chat. Savitri says functionality check. That is right. That's one possibility. Anything else? So I talked about accuracy versus runtime. Accuracy is one of the major advantages of running a simulation. because you don't need to approximate by building a model. You can actually see the full effect of all the devices, all the wires, and you can, if you really want to look at things in detail, simulation is the way to go. So the pre-characterization approach is more for trading off runtime, for trading of accuracy for runtime. And so accuracy is another advantage, or one of the major advantages of running a circuit simulation. Even in the industry, if there are, let's say, some silicon issues, or there are some specific cell level timing issues, which we believe is not right. So the way forward is to set up a simulation, just the small circuit that we are looking to analyze or interested in analyzing, and we run a circuit simulation there. So circuit simulation is for accuracy. So divide and conquer method is more for pre-characterization. It's not for simulation's benefit. It's a benefit of pre-characterization. You basically are breaking down the design into small logic cells, and then you are just running simulation for those logic cells and pre-characterizing them. So that's the benefit of characterization. It's not the benefit of simulation. Simulation takes everything, and you have to run that. Any other questions? If not, then we will resume. Okay, so looks like there's no question. There are no questions. Then we will resume from the point that we stopped at. So we stopped at some of these examples of dot libs, these specific lookup tables for combinational gates. And let's talk about the next set of things, which are sequential elements, and how do we do the characterization of those. So if you remember this diagram, I showed this yesterday. This is from the paper that I shared. So this is a simulation test bench where by this time it should be clear to you that we need to vary the output load. We can vary that. We can vary the input transition or a range of values. The important difference in the case of a sequential element is there will be a control signal, which most of the times we call it a clock pin, and that needs to be the one which should always be a part of the simulation setup, which means we should vary this and see the effect of that on the output. Because a sequential element, if you remember, I showed some curves yesterday where relative data to clock arrival time, there was some behavior on the output. And as we kept data pushing closer and closer to the clock, then the output start failing, right? As also captured in this specific simple timing diagram. So clock signal C, its edge is here. And then data can be changing anywhere in the shaded portion, but it should become stable in this window. And then again, it could be changing. So this window, I need to determine for the given flop circuit that I have. And also, I need to determine whether this window is larger or smaller than, is becoming bigger or smaller based on the various values of my input data transition, input clock transition, rise transition, fall transition, and so on. So this is specifically the input side of things. So here what we're doing is, in this simulation, let's say if I want to see what should be this stable window. The stable window, if you remember, one side of it for a new data it is called setup time. And for an old data, that means I want to hold how long I need to hold an old data. That's called the hold time, THD. T setup is setup time. How early, with respect to the clock edge, a new data must arrive and be stable. Hold, how later after the clock edge should how long after the clock edge should an old data be held or retained for output to be stable, right? So that's something which we can run with this simulation. So what we do, we will fix the clock that is here, and we continuously push the data closer and closer and closer for various different transition values. And then what we're going to see the effect of the data coming closer and closer to the clock on the output value, the Q pin. And if the output value is changing, we will continue to plot it and so on. So this is sort of a very neat view of it. The same picture, but described and shown in a different way. So this is my rise edge. And then I'm pushing the data closer and closer and closer for a fixed input transition. Why is it fixed? Because these lines are parallel. I have picked one value of an input data transition, and I'm just pushing it closer and closer and closer to the clock, and then determining at which value the output starts to show some weird behavior. So for a long time, for a lot of values where data is coming early compared to the clock, the output value is fixed, not changing. Notice this relationship between the arrows. The bold arrows, this clock to Q. And for dotted arrows, you have these behaviors. And then these ones, you start having some failure. The data does not get captured at all in the flop. Output does not change. So this is exactly what is also shown in this plot here. So the x-axis is showing, this is a similar plot to what I was showing yesterday. So the x-axis is showing how the data is coming closer and closer, or relative arrival time of the data with respect to the clock or D2 clock. And then I will keep pushing it closer and closer and closer. For a long time, the output delay or a clock to Q delay will be a constant that is not varying. And then after certain values, it starts getting increased more, and then just basically fails. So this is exactly how any sequential element would behave, latches and flip-flops. Now, this kind of simulation can be run by you by setting up this thing as shown here in the previous slide. And you can fix the data, the clock arrival time, and you can keep pushing the data closer and closer and run a simulation, look at the affected output and plot it. The problem is that because it's a sequential element, you need to run lots of simulations to find out where this weird behavior is happening, right? And which means it's fairly expensive in terms of runtime. And if you have a lot of such circuits to simulate, and you have a lot of combination of input transitions, clock transition, data transition to vary, then that means you need to run. Let's take an example. Let's say you have to run 500 simulations here for one combination of input of data and clock transition values. That means 500 different values where the data is coming closer and closer and passing the clock. So 500 sims required per combination of input transition on the data and clock transition. And if there are 5 clock transition values, possible values, 7 data transition values, then total how many simulations do I need to run? Can you type in the chat if the question is clear? If it's not clear, please say it's not clear. I'll repeat it. But I'm looking for how many simulations in all I need to run to characterize this circuit for all possible clock transition and data transition. If every simulation requires 500, every combination of data and clock transition requires 500 simulations. Is the question clear? Okay, I see no response. If it's not clear, I can repeat this. Let me know. Okay, so what I'm asking is, it's a flip-flop. So which means I need to vary the let's say if I want to measure the setup time, I need to change the data transition. I need to vary the clock transition. Right? That means there are let's say there are 7 possible data transition values. There are 5 possible clock transition values. In addition to these combination of data and clock transitions, I also need to push the data closer and closer to the clock, because that's what basically a sequential elements setup time is, right? It tells you how close you can be so that the output is looking proper. So, and as I showed in this picture, let's say you have to run 500 simulations to find this failing point. That means overall, how many simulations do you need to run across all possible input data transition and clock transition, and multiple simulations that you need to run per combination? So overall, how many simulations do you need to run? Is it clear now? So let me answer it. So we talked about five clock transition, 7 data transition values, every combination requiring 500 sims, which means what? Overall, I need to run 5 into 7 into 500 sims, because each combination requires 500 sims. One combination requires 500 sims. How many combinations are there of data and clock transition? 5 into 7, which means 5 into 7 into 500. So you're talking about nearly 175, or actually 175 00 sims. One 165 35 okay, 175 similar simulations. Is it clear? Total 17,500 sims are required. So that's fairly expensive. That means and if you're going to do it manually, just run the simulation, try to plot this in your waveforms in Excel or some other tool or Python or something. That's going to be not a very efficient approach. So one of the things which a lot of characterization tools or automations people use is something called as a bisection method. Now, if you notice, so the bisection method is basically something which you may have studied about in maybe your in some algorithms class. So the bisection method means that you are doing a binary search. That's binary search is the other name for bisection. So what do? So we fix the we don't need to run so many simulations in a binary search. The way the binary search works is that you fix one end and you start run a simulation. If it passes, okay, then that means you know the boundary of the passing. You know the first value is passing. And then what do? You make a big jump. Let's say you jump on this side equally. Let's say this data to clock arrival time, let's say, is 500 picoseconds. So you make a 500 picoseconds jump on the other side. Since the data is early here, this is minus 500, or you can say plus 500, and this side is minus 500. So you make a jump on minus 500 and push the data after the clock, and you run the simulation. What you see is when you run at minus 500, it's going to fail. So therefore, you know that this side is not a valid point because the circuit is failing. What do? You know you've gone minus 500 on this side, you've gone 500 on this side. So that means now you try to find the middle point. So you come to the middle layer. You come to the middle and you run the simulation again. Is it passing? Is it failing? Is it misbehaving? And you repeat. And you keep doing this. And you if it's a passing point, you mark that as a boundary and you go to the right. If it's a failing point, you go to the left, to the middle, and you keep repeating it. And then in log base 2 number of iterations, you should be able to cover identify the right point where the circuit is failing or just passing. And hence, in very log base 2 number of steps, you are able to find out where the setup time is. So which means in my previous case where I was running 500 sims, I can actually just do so 500 log base 2 500 is what? That is nearly 9 steps. I can just run 9 simulations and I can be done with it. Whereas previously I required 500 simulations, I can just be done with 9 simulations. Which means overall, I need to run only how many? What was 500 earlier now becomes 5 into 7 into 9. And that means I am talking about 35 into 9, which is 45 to 45. 245 simulations are what I need to run. I have a significant speed up. So 245 divided by 17,500. That's that amount of speed up I can do in my simulations because I can use binary search. And that's basically is the method, which is a bisection method or binary search method is used for characterizing the setup time and the hold time or the flip-flops. So this slide just talks about that binary search in more detail. I'll skip this slide. This slide again shows the binary search. You have a pass-fail boundary, and then you keep repeating, and you can converge quickly. So this slide shows an example of how, let's say, a setup arc would look like in a .lib. So setup arc, as we know, see here, is between which 2 pins? Setup is between clock and the data. Both are input pins. If you remember a point I made earlier, a combinational arc, a combinational gate only has arcs between its input and output. A sequential element will have have 2 sets of arcs. There will be an input to output arc, which means like a clock to Q, clock to out, clock to Q, or a data to Q or data to out. But additionally, since there is a sequencing requirement between data and the clock, they need to arrive in specific order and at a specific separation, which means there's also a requirement or an arc between these two. That is a special property of sequential elements. So setup and hold are basically input side arcs of the data with respect to the clock. So after we characterize the setup time or the hold time in similar ways, we could get a .lib. So this is an example of a .lib. So in this case, it's between the D pin and a clock pin, where in this specific cell, the clock pin seems to be called as CP. So let's look at it. The pin is D. Direction of this pin is input. It's a data pin. There are other details. Max transition, what is the capacitance on the input of this pin? Because it's an input pin, it'll have some gate capacitance and some internal layout wire capacitance. That seems to be this value. This value actually is in picofarad, which means this is 0.0018 picofarad or 1.87 femtofarad is the pin capacitance of on the D pin. And then we are looking at a characteristic timing, the timing behavior. And then what are you saying? What is a related pin? So sequential cells, elements have an input pin and a related pin. Related pin is the one which is the control pin or the constraint pin. In this case, it is the clock pin. So with respect to the input, with respect to the clock pin, the input pin needs to meet certain timing. What is that? And here, which timing are we talking about? we are looking at hold. What was hold? If you remember, hold was how long you need to hold or retain an old data for the output to be stable. That means it is after the clock edge. So in this specific .lib, we are the arc is hold and rising. That means with respect to the rise edge of the clock, how long should the data be held? So rise constraint means for input data pin rising, fall constraint means for data pin falling, because data could rise or data could fall, and there could be some separate or different characteristics or requirements for each that's captured in 2 different tables. So hold rising means with respect to the rising edge on the clock pin CP, how long should the data be held? Hold rising. So index 1, index 2, as we saw index earlier, in this case, the index 1 and 2 will represent the transition on the clock and the data. And then for these combination of data transition and clock transitions, there are multiple different hold time values. And these values are negative, which means the hold time is actually pretty good, which means data can be released well before the clock. It doesn't need to be held after the clock. If it was after the clock, this value would have been positive. That means this flop has a good hold time. This is a fall constraint. That means for the input pin, when it is falling, what is the hold time? It's different than the one where the input is rising. But again, it is, most of the values are, or all values are negative, which means again, the data can change well before the clock edge. That means again, it's a very good hold time. So any questions here? You can type in the chat. Okay, so we talked about, so I see some question here. How are values for the characterization chosen? Okay, so Bhaskar, you want to unmute yourself and be specific about what you're asking?
Sir, for the input transition and the output capacitance values.
How are they chosen?
Yeah.
Yeah, that's a good question. I mean, in the case of a combinational gate, it will be, or combinational arc, it will be input transition and output load. In the case of a, let's say a setup time or a hold time, it will be data transition and clock transition. So the question which Bhaskar is asking is, how do we decide on these values? That's a good question. And usually, depending on what the tool may be, or the which company it is, they usually have some methodology at their end where they may say that, okay, this operating voltage where I'm running the simulation, my usual clock periods or clock cycle times are these numbers. So I can possibly use some percentage of clock cycle time as input transition values, and I can go from a very small value to a very large value, and I can set them. Or a lot of times, let's say if you are creating your own .lib, you can come up with your own combinations. So the tool, it's just a simulation setup, but usually, for example, companies where I work, companies I worked in, there is an actual elaborate flow which is used to determine how to get these numbers, and that's usually based on which operating voltage the simulation is being run at, what kind of cells there are, what kind of threshold voltages the cell may have, and based on that, some of these values would change. But at your end, let's say if you are running the simulation and you are trying to create a .lib, you are free to choose any possible combinations, as long as you don't have too many points. Let's say here there are only three points. You should not have very few points, and you should not have a lot of points. Having a lot of points defeats the purpose of creating pre-characterized models, because then you have to run too many simulations. Having too few points means the accuracy of the simulation, accuracy of the model is not good, because if you just have 2 points, it's basically just a straight line point, the linear thing, right? So there should be a balance. So somewhere between 4, 5 to 7 values could be chosen. And so which means any table which is having somewhere between 20 to 35, 40 points is fairly reasonable. And you need to ensure that the points are fairly spaced out. You can't have a lot of points sitting very close to each other and one point very far off. So if you space them out uniformly, that's also a good approach. So you could follow one of these approaches. Does it answer the question?
Yes, sir.
Okay. Yeah, that's a good question. And in case, let's say you run a simulation, this is something which you could try at your end, and you can see the effect of what's going to be the effect. Let's say if you don't choose the points properly, or let's say you have a lot of points at very small transition values or very small load values, or at very large transition values or very large load values, you would see that the accuracy of the simulations or the results would be going down. Okay, any other question? You can type in the chat. Okay, I think if there are no more questions, then maybe we can discuss during the break, the last break. So let's continue. So what is the benefit or the main and the importance of characterization? So characterization specifically from an ASIC flow, but characterization applicable in a lot of other kind of designs also. FPGA has its own kind of characterization, but not the way that we discussed today, but the specific kind of characterization that we talked about here, which is a cell-based characterization, is a characteristic of ASIC design flows. So ASIC design flows, for digital ASIC design flows, do not use any circuit simulation. So most of the timing power is analyzed using these pre-characterized models or .libs, and that is used in multiple different steps of the flow. So you may have heard about synthesis, placement, routing that I touched upon briefly in the introductory session. So all these steps require the standard cell library or the pre-characterized library. So this cell library is passed as input to these steps, and all the analysis for power or timing, that means for performance, for races, and so on, requires the availability of these models, these .lib files. So this is essential for an ASIC design flow. And it is a fairly well understood and a polished methodology. It's been used for almost like 30, 35 years, and it's only improving day by day with more advancement in understanding how to model some of these complex behaviors of these gates, their transition profile, the delay profiles. Better modeling is happening. You can now improve the accuracy of the models with respect to SPICE, and also with newer type of transistors and more complex phenomena showing up in the process. We have more and more complex effects being captured in the characterization. As I was showing here, if you remember, there are a lot of things which are captured in the characterization flow. Part of this, all these complexity, is because with advanced process nodes, a lot of new and complex effects are showing up, which needs to be characterized in the .lib. Because since you're not running simulation, there needs to be a model for a lot of these effects, which the analysis tools need to be able to refer and then run a modeling exercise and be able to predict whether that's going to be a problem, whether the chip is going meeting its spec or not meeting its spec, or the circuit is meeting its spec or not meeting its spec. That's one of the reasons why we have so many different parameters being characterized. So it's a well understood thing, and it's something which is the heart of the ASIC flow, standard cell library. and something which I think will be a good exercise for you to spend some time maybe thinking about what we discussed today. And if there are any questions, maybe we can bring it up either tomorrow or on the last day. Okay, we talked about characterization and how it's useful and specifics of characterization. Let's talk about some very important concept from actual chip design point of view. So when we usually run circuit simulations, right? We don't care about what is actually happening when the chip, when the transistor or the circuit or multiple different circuits or the whole chip behavior looks like, because a foundry or a fab does not just print one transistor for you. It does not print one gate for you. It does not print only a circuit for you, or does not print just one chip for you, right? It actually, for example, for you to have it profitable, we talked about how ASICs require a very large volume to be profitable because the whole NRE or the fixed cost is so much. So the whole idea of going to and building an ASIC or an ASIC SoC is because you want a large volume, which means you're going to have lots of different chips coming out of the foundry or the fab. For example, Qualcomm, Samsung, MediaTek, AMD, Intel would be getting millions of chips of a specific kind for a specific specification or a market or a category, like a GPU, CPU, or for a mobile GPU or a mobile CPU or a server CPU or a server GPU and an accelerator or whatever, right? So they could, and they need millions of them. Now, which means there is a basic phenomena which happens, that it's a natural thing. When you're making something in large batches, in large volumes, from one instance of the chip to the next, to the next, to the next, right? As you keep comparing them, they are not going to be exactly identical. This is a natural phenomena, right? There's going to be randomness. There's going to be some sort of a uncertainty in the way things are happening. The whole process is going to have some uncertainty, some randomness. When I say randomness, it means it's not something which is intentionally done by the fab. It is basically like, it is just the law of nature, right? When you're doing something for a lot of time, the results are always not exactly the same, right? For example, let's take a very crude example, right? You're trying to shoot a bullseye. You're even if you're an extremely skilled shooter, you're going to have your shots spread out around the bullseye, and a few of them are going to hit a bullseye. To call you a very good shooter, you will be hitting the bullseye a large percentage of times and missing the bullseye a small number of times. Same way, a very good foundry or a very good fab will have a large percentage of chips meeting its spec, but a few of them would be away from the chip, from the spec. And in some cases, the spec, it could be away from the spec by a large margin. So this is a natural thing, and it is something which people who understand statistics, who understand the fact that there is natural variability in these things. For example, you're buying one shirt, a cloth factory is making t-shirts. Every t-shirt is not going to be identical. Some of them are going to have some thread sewn differently. Some of them are going to have pockets slightly different. I mean, it's like a natural thing. It's something which is very well understood by people who work in factories, who in foundries, who look at things in large volumes. They know that this variability is law of nature, right? It's part of the process. Same way, when you're doing chip designing, it is something which you have to account for, and it's something which you have to consider when you are designing the chip. Why? Because you may think that, okay, my chip meets the spec. I'm going to assume some channel length value, some width value, some threshold voltage value, and even some supply value. And I'm going to assume some propagation delay or some current. But in reality, it never happens like that. It is actually a distribution. You may have studied some statistics. If you remember that, what's a distribution? Distribution means if you're looking at studying some phenomena or some variable or some parameter, it's going to be spread out around some mean value, right? That is a distribution. So each of these things will be a distribution. L will be the channel length will have a distribution. width may have a distribution or will have a distribution. The oxide capacitance would have a distribution. Threshold voltage would have a distribution, which means since each of these things are a distribution, my propagation delay is also a distribution, which means my current is also a distribution. So which means I have to consider these effects and I have to account for it and study what's going to be the problem or negatives of this and how I need to margin it or consider it so that my chip still meets my spec. That is the whole concept of PVT, process voltage temperature. Now, it is basically an effect of variation or variability in the whole design process. So what are the process parameters? When I say process parameters, are something which is controlled by technology. What are those? As we saw in the like couple of days back when I was talking about delays and currents, mobility, mu, oxide capacitance, threshold voltage, channel length, number of fins if it's a FinFET, wire width and spacing. All of these are technology parameters. These are printed by the foundry on the chip. These may have variability. There could also be system level and architectural variables which could vary because, for example, your power supply at home could also fluctuate. There could be power surge, there could be power cuts, there could be power droops, right? Let's say you are living in a very warm city, and it's, let's say, a specific day is especially warm, and almost everyone in your locality is using an AC, which means what's going to happen? The whole the grid, the power supply is going to be drooping. Why? Because there's so much load there, right? AC, all these motors and all these inductive devices have introduce a lot of load in the power grid, right? So which means they're going to be droop. The whole power supply is going to drop. Same thing on a chip could happen, where the supply could actually be drooping because there could be a lot of activity happening suddenly, and therefore some sort of inductive effect could happen. There could be some resistive drops happening, which means voltage could be lesser. And then additionally, there could be other things. For example, on my motherboard, where I have a voltage regulator, that could be misbehaving and things of that sort, right? So which means from a system level also, there could be parameters like voltage, which could be going up and down or varying. So design layout variables, again, a lot of these things could have some variability because when I'm designing, at some point at a specific time, when I'm designing, I could have designed in a specific way, but later I may have decided that, okay, that's not a good way to implement. I could change it, which means from a run to run, from iteration to iteration also, I could have some changes. So in a sense, a lot of these things are introducing variability. So when we are designing chips, we look at these parameters: process, which is coming from technology; voltage, which is basically effect on the voltage coming from anywhere, on chip, off chip; and then temperature. Why temperature? Because let's say you are running in a data center, let's say a server farm, let's say Amazon's server farm, right? There could be a server which could be running at full frequency, full throttle, which means high frequency, full throttle, extreme amount of load on that, which means it could be getting heated up, which means temperature in that whole chip could be around 100 degrees Celsius. Or there could be another chip where it's sitting in, let's say, Iceland, where there's very minimal activity, but only a few circuits are switching. The temperature could be somewhere near 0C or even slightly lower. It should still function. But that Amazon server farm, that high activity chip should also function. The voltage could be changing. It should still function, and all these things. So that's basically the concept of bringing in this process voltage temperature corners. Corner means it's sort of a combination of process, voltage, and temperature, and you create this combination, and then you run simulation around that. So in the case of process, which is coming from the foundry, there are going to be some effects which will make the transistor faster. there could be other effects which could make the transistor slower. Let's take an example. If I increase the VT, what's going to happen? The transistor is going to get slower. If I increase the L due to the variation, the transistor could get slower, right? So which means I could have certain instances of transistors or circuits where they could have slightly higher channel lengths, slightly higher VTs due to the process variation, and that specific circuit could be slower. So I have to account for it. And that slow circuit is called the slow corner. Complementary, I could have a case where VT could be smaller due to variation, L could be smaller due to variation, width could be more due to variation, and the transistor could, the circuit could become faster, and that is sometimes called as a fast corner. And then when the transistor and the circuits are meeting the spec, it's called a typical corner, typical process corner. So when people are saying fast, typical, and slow in this specific picture, this is what it means, as I described. Due to process variation, some natural variability, you are having some gates becoming fast, some of them becoming slow, some of them are meeting the spec. So delay, as L increases, as I just described, is going to be going up. So for a slow transistor, there could be an effect where the L has increased to such a large value, the delay has become worst, and so on. Similarly, you could look at temperature, and there could be an effect of that. The temperature is interesting because temperature has two parameters which are affected. Temperature could affect mobility, temperature could affect threshold voltages. Can people type in the chat explaining how temperature affects mobility of a transistor and how temperature affects threshold voltage of a transistor? What happens to that threshold voltage when temperature increases? What happens to threshold voltage when temperature decreases? Can people type in the chat? Am I audible? Okay, so Bhaskar is responding, mobility increases with temperature. Mobility increases with temperature. Okay, mobility increases with temperature. When you say mobility increases, that means that transistor becomes faster. Harshvardhan, can you unmute yourself?
Yes, sir.
So when you say
Like more
mobility
number of
increases,
like more number of electrons like come near the channel.
okay, so when you say mobility increases, do you mean the transistor becomes faster, or do you say transistor becomes slower? Can you answer? Do you think the transistor becomes faster or slower? Harshvardhan?
Slower.
Slower. But you're saying
Yeah.
the mobility increases. Mobility is directly proportional to the current, and current is directly proportional, inversely proportional to delay. So if you're saying mobility increases, then it should become faster. That means the delay should decrease.
Like
But you are saying
there will be a certain saturation limit, right, sir? Like after saturation limit, there won't be much movement between the electrons.
actually it's a reverse effect. Mobility degrades. Why? Because think about this, right? There are thermal effects. Thermal effects means as temperature increases, the whole channel, the substrate is going to have oscillations. The silicon atoms are going to start vibrating more and more, which means they will have more collisions with the carriers, which means mobility is going to drop with temperature. It does not increase. And that's one of the reasons why you have a higher resistance with increasing temperature due to mobility degradation. So which means mobility degrades means you have potentially a slowdown. Potentially. Why potentially? Because I don't know what's going to be the effect on threshold voltage. Can people type what is going to be the effect on threshold voltage as temperature increases? So with increasing temperature, what happens is there are going to be more defects in the silicon substrate, and which means you get more free carriers. So more free carriers means current potentially increases. So it's like a compensating effect. They have opposing behavior. So mobility degrades and is trying to slow the channel down. The VT is dropping because I have more free carriers available. So now, which means depending on whichever has the higher weightage, it's going to have an effect. And usually, if it's high temperature, it's dominated by mobility. And if it is low temperature, it's dominated by threshold voltage. And that's basically the phenomena. In the latest advanced technology nodes, what is seen is at high temperature, we have mobility dominated effects. At low temperature, we have VT dominated effects, which means if you are slowing down, if you're going to a lower temperature at low voltages, the VT effect is dominant. As you're going to high temperature and high voltages, the mobility effect is dominant. So that means at low voltage, low temperature, and a high voltage, high temperature, both these combinations of voltages and temperature, the circuit slows down. Okay, so in this picture, even though it's shown that the temperature, the delays tend to increase, it all depends on what is the voltage and what is the temperature. But in principle, if it is mobility, this picture is right. If mobility is degrading with high temperature, therefore the current is dropping and the delays are getting worse. Now that's the concept of PVT, and since we have this variability, we have to analyze at all these combinations: fast, slow, and typical. So another concept of variability is the sensitivity. Now, when you have variability, you have things which are changing. Therefore, you need to understand what is the effect of that. Is the effect of that large or small? And do I need to worry about this? And there's this concept of sensitivity. Concept of sensitivity means is, let's say if I'm talking about, if this is the equation of delay, right? So the equation that we've been discussing. Now, that if we are looking at what is going to be the effect of process variation on the VT or the threshold voltage variation coming from the process, the foundry, the process, what is the effect of that? How sensitive is delay to change in VT? That is something which I can analyze with a metric called sensitivity. What is sensitivity? If you notice this seems like some complex math, but if you break it down, it is fairly simple. You have delta VT and then VTH in the numerator. I can bring this VTH down here. You have delta gate delay and then gate delay in the denominator. So delta gate delay by gate delay is nothing but what? Percentage gate delay or percentage change in gate delay. Delta VT by VTH is percentage change in threshold voltage around over the typical value. So that means sensitivity is nothing but what is the percentage change in the quantity that you are analyzing, in this case gate delay. What is the percentage change in gate delay for the percentage change in threshold voltage? And that, if you simplify this equation, it comes as this. So this equation actually shows that VTH has a very large sensitivity on gate delay. For even minor changes in threshold voltage, there is a very big change in gate delay. And therefore, we need to be concerned about threshold voltage variation when we are considering delays. This is another example. This is from a 65 nanometer and older technology, somewhere in the early 2000s to mid 2000s. This is showing how the frequency of various chips, each dot is representing some silicon chip, let's say a CPU. And the x-axis is the chip leakage, how it is varying. What you'll notice is that, as I said, since it's coming from a foundry or a fab or basically a factory, which means you cannot guarantee every chip is going to be identical. And this is clearly a good example showing that there are some chips which are so the x-axis, the y-axis is showing the frequency, how much it's changing or varying. X-axis showing the leakage. It's normalized, which means with respect to mean. So if you notice, some of them are very slow. Some of them are very fast, almost 30% fast. A lot of them are sitting somewhere here, as expected in a distribution, right? And if you notice leakage has a huge spread. Some of the bad or highly leaking gates are as high as 25 times from the minimum value. The leakage spread is 25x. The delay spread is around 1.3x or 30%. This is again a very a well-known phenomena in the last few years. We see this very frequently when we in the industry, when we look at chips coming from the foundry. We see this invariably, and we have to do something to handle this when we are designing, so that we can account for this and manage this. So I shared these two papers in the links in the chat earlier at the start of the presentation. These are two good papers which talks about process variations and the effect of that on digital circuits. These are slightly advanced papers where I think maybe master students and faculty members can read and maybe simplify and try to engage the interested students. So these are good papers, and I would suggest that you can probably try to start reading it. There are also good references, as I said earlier, yesterday. A lot of these papers may not strike you immediately, so maybe you can start reading the abstract and the conclusions and some sections which you understand, and then go to the references, see if you can find some simpler papers in the references, spend some time there, come back to these papers, and you will have a better understanding. So spend some time. I think in probably a few weeks, you should be able to get these, understand these papers. And these are some really good papers. These are classic papers to understand the effect of process variation across different chips as shown here, and also within the chip. Even within the chip, there will be some process variation because there could be different circuits. The same circuit, when it is used multiple times within a chip, again, due to variability or variation, they will be behaving differently. And there could be some effect of that. We need to account for it. That's captured in these two papers. I think that's all I had for today. Let's, and I'll end here. Any questions? Let's open up for questions. Feel free to ask if you have any questions from what we covered today, and or from any items, topics from yesterday, or any other points you want to discuss. Feel free. Jitender has a question. Jitender, you want to unmute yourself and ask? Hi, Jitender. If you're able to hear me, can you unmute yourself and ask the question?
Hello.
Yeah, go ahead, Jitender.
Sir, as we know, there is a number of second order effect are there, and VDH, gate voltage and threshold voltage, these all things are depend on some parameter, some different parameter as per the equation. Hello.
Yeah, I can hear you. Please go ahead.
Temperature is the one of the factor. No? There are a number of different other factor also which we have to consider to before designing the hardware implementation. Yeah, for proper IC design.
Yeah, I mean temperature. I talked about temperature. We talked about process. We talked about voltage. These are the major three factors which typically are used. We talked about these PBT corners, if you remember, if you were following the discussion.
Yeah.
You have any specific
Yeah,
questions based on this?
There are a number of things are mentioned in the book also, like second order effect. So our knowledge is limited to that potential also, that point only. And there are basically, I want to use cadence or synopsis tool. There are a number of other parameters which we have to mention before the designing, na?
Which parameters specifically? Can you describe?
Rather than its length, width, and size of metal, like for which temperature we are want to work it, or how much threshold voltage, or there are
Yeah, threshold.
many.
Yeah, threshold voltage is not in your control. That comes from the transistor model. So the width and length, if it's an analog circuit, length is controlled by you. If it's a digital circuit, usually length is fixed. So width is controlled by you. So these are design parameters, right? If you remember, I talked about these, and we sort of categorize them into these categories. There are technology variables, and there are system variables or architecture variables, and there are design variables. So design variables could be things like width, number of fingers, block size, wires, width and spacing. All these things could be controlled by you. All of these things have an effect. And all of these things are going to have an effect because they determine what's the load, how quickly the circuit can switch, therefore how much current it can draw at a given rate. Similarly, voltage determines how quickly the transition happens, which means determines the current. And then how big the block is, how the complex the architecture is, determines the load capacitance. Similarly, technology variables, these are coming from the models or the foundry, all these parameters. So all these things have an effect. So the one that you can control as a designer are primarily these. If you are an architect or a system person, you can also include these variables. So in a sense, these two are non-technology parameters. These are technology parameters. So the actual equation, this is obviously just a very simple equation, right? Because no one knows what in reality the details are, because there's no value in writing a proper equation here, because finally people run simulation. The reason for showing this equation is for you to develop an intuition of how the whole thing behaves. Because finally, if you're going to build a product, you have to always run simulation, right? But before simulation, you need to have an intuition. You need to be able to say that, okay, this is the dependence on this variable. If let's say there is a lot of variation in threshold voltage, I need to worry about the effect on delay. This simple model tells you that. And that's what typically sort of smart engineers do. They always find the right balance between simple models versus a full-blown simulation. So first you need to build an intuition, a good mental model, which some of these equations give you. And you can do a quick analysis. And then you can say, okay, this circuit will work or not work. And then once you've decided on the circuit, you have to go back and run a full simulation. Probably you'll build a layout, you will extract it, which means all the parameters that you are there in the layout are showing up in the extraction. And then you run a full simulation across various process space, fast, typical, slow, and so on, across different temperatures, and you can see the effect of that. That usually is the full design approach. Does it answer the question?
Yes, sir. Sir, one more thing.
Yeah.
Sir, in the last couple of days, you told me that the size of PMOS and NMOS should be in a proper, it should be designed in a proper way, that the PMOS size must be a little bit greater than the NMOS size.
No, I didn't say that. What I said was,
Yeah.
what I said was, usually in textbooks,
Yeah.
right, or in older technology notes, very old, like almost like 25, 30 years back, right? Even let's say even 15 years back. So PMOS was because whole mobility is around half of the electron mobility. Therefore, if you want to have the same resistance for PMOS and NMOS, you have to widen the PMOS 2 times than the NMOS. And that's why we had that ratio of 2:1. That is again a very textbook thing. In the latest technology notes in FinFETs and so on, the number is very close to 1.1 and 1.05 or something like that. So it all depends on what kind of transistors you have, which technology. But yes, based on this mobility ratio and the relative drive capabilities, you have to size the circuit if you want to have balanced rise and fall times, is what I meant.
Okay, sir. Sir, I have microwind. Hello.
You have?
I have microwind only. So whenever I try to design a large circuit, when I increase the size of PMOS, then the load capacitance is decrease. The output voltage is almost flat. Uh, then try to increase the load capacitance, then the output waveform is become normal. So the size of gate leads to the load capacitance also.
Yes, size of the gate can lead to an increase in load capacitance, as we saw earlier. As I think someone was asking, it was Pawan, I think. He was asking what is the effect of load, and if you remember, we talked about this. Yeah, we talked about how I think this was in the previous lecture, the talk, where I showed how the overall load on the output is not just the load coming from the other gates which you're driving and the other wire, but also the gate's own self-loading from its own diffusion capacitance, its own wire in the layout, which means that the gate becomes bigger, there will be proportionally higher diffusion capacitance, which means higher parasitic capacitance. So the self-loading will be higher. But because its drive increases, it compensates for it.
Okay, sir. Thank you, sir.
All right, thanks. Any other questions in the chat? Sri Lakshmi asks, number of sims depends on what? The number of sims depends on how many combinations of process voltage and temperature you want to run at. If let's say there are 3 process points, as we saw here, fast, slow, and typical, let's say 3 process points, let's say there are 3 voltage points, low voltage, medium voltage, and or high voltage, which means, and the temperature, there are 2 points, 0C and 100C, which means how many combinations? 2 temperatures multiplied by 3 voltages, which is 6 multiplied by 3 process points, which is, so 6 into 3, which means you need to run somewhere around 18 simulations to be able to reliably say that the circuit works properly or is meeting the spec. Something like that. It all depends on, this is the concept of a process voltage corner. You may not need to run all simulations, but this is like one very crude way of saying I need to run so many simulations. Usually the number of simulations is actually smaller because you need to look at how the trend of the delays are and whether you need to meet specs at all these process corners or not. As long as you know which are the worst process PVT corners, and if you decide them that these are the worst, you could just run simulations on those. So it all depends on whether you know the specs and at which corners PVT combination you have the worst specs, and run simulations there, and we'll see whether the circuit delay is meeting the spec, whether the circuit leakage or dynamic power is meeting the spec at those points, and things like that. So that basically determines how many sims you need to run. Okay, I think we have run out of time. It's 9, crossed 9. If I'll probably take one more question, and I would suggest you to refer to what we have covered so far. We'll discuss static timing analysis and power analysis tomorrow, and some aspects of optimization. Should be interesting based on all the concepts that we have.
Hello.
Yeah, please go ahead. Yes.
Sir, this is Chandrasekhar from ISO.
Yes, sir.
Hello. Sir, are you available on Monday also, sir, in the GMIT campus? Because I need to meet you personally.
No, I will not be. I may not be able to visit. I'm actually working here in Bangalore, so you can probably try to send me some questions to the organizers, and I'll try to answer your questions.
Definitely. At the end of this week, I'm going to post the questions, sir. Okay.
All right. So thank you to all of you, and thanks for being an attentive audience. Let's try to meet tomorrow. Should be some interesting sessions, topics to cover, and should be an interesting session. Meet you all tomorrow. Thank you. Bye.
Thank you, sir. It was a very informative session. Thank you. Thanks to all the participants. We will meet tomorrow. Thank you.
Thank you, sir.